Hello, welcome to our channel. Okay, thank you for joining us. So, in this video, we want to look at numerical methods for partial differential equations, right? And we are going to look at how we can get the exact solution, right? Through the question here. Okay. And I must make mention of the fact that this is university mathematics. It's meant for university students. Okay. Those that are doing the numerical partial differential equations or numerical methods for partial differential equations. Okay. And we want to look at how we can get the exact value. So we are saying compute the exact solution for the heat transfer boundary value problem of a load of length 1.0 centimeter given by this differential equation, d2t to dx squared minus beta squared t is equal to negative beta squared ta. So this is ambient temperature, all right? This is the ambient temperature where beta squared is 16 square centimeters and ta is 20 degrees Celsius. Then you have the boundary conditions are T of 0 is 25, T of 1 is 75 with step size of 25. Okay, so how do we find the exact solution? All right. Okay, so how do we get the solution? The first thing that we can do is to rewrite maybe our differential equation. Okay. We can rewrite it in this form minus this is the minus, we can say beta squared t is equal to minus beta squared ta. So upon doing the substitution, so we have got t double prime minus beta squared is 16. So we have 16t is equal to minus 16, then ta is 20 times 20. Okay, so this will give us t double prime minus 16t. We're just trying to derive it, get negative 320 as our differential equation. All right. Now we've been told that t of 0 is 25. Then t of 1 is 75. Our step size is 0.25. So what does it mean? From here, we know that our lower limit is 0 and our upper limit is 1. Therefore, we know from the formula for the step size, which is b minus a divided by h. So what does it mean? This implies that our h, of course, we know our h, our h is a 0.25. B, in this case, our b is 1. Okay, so 1 minus 0 divided by n, the number of intervals. So therefore, n will be 1 over 0.25. Okay. Therefore, what is our n? You get your n to be 4. This is our n. Okay. So now from here, we discretize the interval. So we can say discretization. How do we discretize the interval? So you can draw this with a ruler. Okay, so okay, so we are going to have, so we'll start with x naught. X naught here is 0. Then the other one here will be x1 is 0.25, the step 5. Then we'll have 0.5, 0.5, then 0.75, and lastly we'll have 1. So I from 0, 1, 2, 3, 4, which is our end number of intervals. Okay. So when we talk about x naught, so what that means is that, what does it mean? Our x naught is 0, our x1 is 0.25, our x2 is equal to 0.5, our x3 is 0.75, and our x4 is 1. Okay. Okay, good. Now we want to do an exact solution. Okay. We do an exact solution. So we have t double prime minus I think 16t from our expression, and just confirm the actual expression. Okay, let's check the actual expression. Yeah, minus 16t is equal to negative 30. This is what we wrote. Okay. So so we are going to so say let t double prime minus 16t be equal to 0 for now. Deal with this as a homogeneous differential equation. So now, how do we work out this? So we are going to have, we express it in this form, m squared minus 16. This is equal to t, meaning that if we had, suppose we had t double prime minus 16 t prime, okay, maybe plus t. We are going to express it in this form. So each derivative is m, maybe in that way, but we have the second derivative. So we'll put m squared minus 16. The derivative here is m plus, okay, just like that, actually. All right. So it should be comfortable to express it in this form. Okay. So you should be able to express it in this form. So this would be equal to 0. All right. Okay, now let's get back to what we have here. So this is our form that we have. So we have got m squared minus 16t, the coefficient of t here. So when we solve, we have m squared is equal to 16. Therefore, m is plus or minus what? 4. So you can see that these two roots are different. Okay? These two roots are different. Therefore, the complementary equation. The complementary equation to be TC is equal to C1, if you remember this, C1 E R1X plus C2 E R2X, all right? Okay, so this implies that our TC is equal to C1 E, our first root is 4X plus C2 E, our second root is negative 4X. This is what we have. All right? This is what we have. Okay. We can also deal with the particular solution, that is TP. So what that means is that we express, we are going to say TP is equal to A, all right? Okay, why are we saying TP is equal to A? You look at what is on our right-hand side here. You check what is on our right-hand side here. It is a constant. If on our right-hand side here we had maybe x squared plus 3x, then our TP would have been maybe ax squared plus bx. This is the form. Okay. That is our form. Okay. That's our form. So we proceed. So in this case, because there's a constant, we have that. So we are going to say T prime is 0. T double prime is 0. So now we substitute it into the equation. Okay? Which equation? We are going to substitute it into this equation. Take note. The original equation, which is T double prime minus 16 T is equal to negative 320. Okay, so when we substitute, what is our double prime? 0 minus 16 T is equal to negative 320 here. Okay, so therefore, negative 16T is equal to negative 320. So when you divide T take note, we said TP is A, okay? TP is A. So here, we are going to put A here, okay? We're going to put A, so this is our A, and this is our A. So our A becomes 20, okay? Our A becomes 20. So now, our general solution, T of X, supposed to be the complementary equation plus the particular equation, like this. So, what are we going to have? Here, we've gotten this to be C1 E4X plus C2 E negative 4X. And then our TP is 20 now. because here we've said TP is equal to A, and our A is 20. So our TP is 20. So plus 20. This is what we have, 12x. This is our general solution. Okay. This is our solution. Okay. This is our solution. Okay, let me share the screen. Okay. So now, we can now apply the boundary conditions. Boundary conditions. The first one is T naught is 25. All right? So what does it mean? You're going to say C1 E4 when you put a 0 here, plus C2 E negative 4 when you put a 0 here, plus 20. The answer must be equal to 25. Okay? So what does it mean? We'll have C1 because this will be 0, right? So C1 plus C2 plus 20 is equal to 25. So therefore, we can express C1 in terms of C2. So C1 is equal to 25 minus 20 minus C2. Therefore, C1 is 5 minus C2. All right, this is what we have for C1. Okay, then we can also apply T1 is equal to 75. Okay, what does it mean? We are going to have C1 E4 times 1 plus C2 E4 negative 4 times 1 plus 20, and that this should be equal to 75. All right? But what is C1? Okay, if you want, we can simply say this is C1 E4 plus C2 E negative 4. This is equal to 55, all right, when you subtract. But what is our C1? Our C1 is 5 minus C2. So this is what you have. E4 plus C2 E negative 4 is equal to 55. All right? So when we distribute, what do we get? When you distribute, you're going to get 5 e to the power 4 minus C2 e to the power 4 plus C2 e to the power negative 4. The answer is 55, right? So we can keep the C2 here, negative 4. This will be 55 minus 5 e to the power 4. Okay, we can try to factor out C2. We have negative e to the power 4 plus e to the power negative 4 is equal to 55 minus 5 e to the power 4. So, therefore, C2 is equal to 55 minus 5 e to the power 4 divided by negative e to the power 4 plus e to the power 4. Now, what is this when you compute? This implies that C2 is equal to, when you work it out, you get 3.993979 692.04. This is what you are going to get. Okay. And hence, what is our C1? C1 will be equal to 5 minus C2, 3.993979692.04. Okay. Therefore, C1 will be 1.00020 307.96 when you work it out. So we are going to replace it now into our general solution. Okay, therefore, what do we have? T of x is equal to, when we replace, we have got 1.060203079.6 e to the power 4x plus 3.993979692.04 e to the power negative 4x plus 20. This is our general solution. Okay. Now, we need to find the solution now. What is the value of T1, T2, so on and so forth. So, if you say T naught, so when you put your T naught, and remember from where we said our T naught was 0, I can take you back here. Our T naught is 0, so on and so forth. Take note of the discretization now, it will be applied here. So when you put your 0 throughout, your T naught will be 25. All right. Then our T1, what is X1? Our X1 is a 0.25. Okay. 0.25. So when you replace here 0.00602030796 E4 0.25 plus 3.9939796940204 in negative 4 times 0.25 plus 20. It simply means your T naught will be, your T1 will be 20.2039. Continuing in this manner, T2 will be 27.9741. You can counter check because T2 here, for T2, take note, X2 is a 0.5. Then T3, your T3 here will be 40.4053 because your X3 is 0.75. You substitute there. Then T4 will be 74.9999. So when you round it off, this is the same as 75. Why? Because our X4 is 1. So those are our solutions now. That T1 is 25, T2 is T naught is 25, T1 is 24.2039, T2 27.9741, and check that. T3 is equal to 40.4053. T4 is 75. That is our solution according to the step size. All right. Thank you. That's where we end for this presentation. Please subscribe to Ambanpiri JM. Till next time, in case you want to contact us, you can contact us 0978 56 58 76, 0979 67 38 09. Till next time, bye-bye. God bless.